Okay, welcome to the study hall for August 11th. Today's topics are, for the most part, holdovers from what we didn't get to last time. Those are unit conversion problems in quant. They're all quant. Unit conversion problems we didn't get to last time. Rate problems with hypothetical cases. We've pushed this topic up here because there's one or two people taking a test pretty soon that have asked about it. And then if time permits, we'll do mixture problems. If time doesn't, mixture problems work actually very well with this other topic. So having these in the same lesson is a good thing, because they may not look like they're the same type of problem, but what you'll discover eventually is that they actually are. So these are going to be synoptic. We should be able to get to all of these topics today. If not, then I guess we get to bump the mixture problems again. So we'll start with unit conversions. But first, as usual, we have to start with the warnings that we always give. So let's do that. Submissions, remember the qualities of submissions that are not so hot. People have been improving on this recently, and I think the reason is that the Thursdays homepage itself has become a little bit more explicit about these things, mostly because I've bothered the content people until they've made it more explicit. But still, some people are giving the kinds of problems that you shouldn't give, and what I mean by that is some people are giving problems that are way too general, like they're saying things like, how do I do geometry? Or even, how do I solve problems faster, which is basically the entire GMAT at once. You know, we can't really do things like this, not because we don't want to, but just because they're not possible. I mean, there's a reason why we have a several hundred-page strategy guide for geometry, and why we have like thousands of pages on the whole test. So we can't treat them in a single swath. Also, this is the problem that people have more. People are too specific. If you have a single problem and you just want to know about a single problem, the place to have that addressed is the forums, not here. So if you just have a single problem and are like, I don't understand choice D, then the forums exist for that exact purpose. And, you know, frankly, you'll get a response a lot faster on the forums than you would if you had to sit and wait for it to be in the study hall. So don't submit things that are too specific. Instead, and also don't submit personal issues. Personal issues belong in the forum. We do have a folder designed for that, the exact type of thing, which is our general questions folder. So what we want is, again, we want a topic of intermediate depth. Like today's topics are good examples of topics. Unit conversion problems is not a single problem. It's a theme. But it's also a theme that is tight enough to be covered in a segment of a study hall. It's not like saying geometry, where it's this vast topic that you could not hope to cover. So same sort of thing with this. Like rate problems with hypothetical cases is a very nicely defined topic. So is mixture problems. These are very tight subjects of intermediate depth. So this is the kind of thing that you want to submit. It's okay to give a problem as an example, but if you give a sample problem, you need to generalize. You need to tie your problem into a more general question. If your problem is super duper specific, what we'll basically tell you is just put it on the forum, please. Finally, no problems from the official guide. I think the page actually doesn't allow people to submit these anymore, but do not submit problems from the OG. Also, please do not submit single questions with no larger context. Please put these on the forum instead. Because remember that the forum allows exactly the same sources that the study hall allows. So anything that is legitimate for the study hall can also go on the forum. So if you have anything that's super specific, that's what you should do. Finally, please check the archives. In the last couple of weeks, we've had people asking about things that have already been very thoroughly covered. For instance, we had someone ask, can you do a session on probability? Well, we've already done a session on probability, and that was on February 17th of this year. So, I mean, here's a guideline here. Please check the archives, and if you want to submit a topic that has already been covered, because I mean, sometimes we'll revisit topics if there is something new to talk about. Because I mean, if there's some new angle that we can go at it from, then we'll do that. But if you want to submit a topic that has already been covered, then you need to say what you want to cover. Then like, please specify in your submission what aspect of that problem has not already been covered in the previous study hall. So in other words, like let's say that, so like this is an example. One of today's topics is rate problems with hypothetical cases. We did do a study hall on rate problems, but then the student who submitted this case said, okay, I'd like to see an emphasis on hypothetical cases, which wasn't really the emphasis of the last section. So even though we have done rate problems, we didn't do rate problems with a particular focus on this aspect of the hypothetical. And so that makes this a legitimate submission. Whereas if somebody said, I just want to do rate problems, then that's not, because we've already had a study hall where we did that. So make sure you guys see the difference. So like smiley face, if you understand this. Smiley face icon, the button that's over there. Because again, we've had 40 sessions. So if you just submit a kind of random topic, the chance that we've covered it already is fairly high. So please look through the archives. And if you find the topic you're asking about, then of course watch the session. And then if there's something that's not in there that you would like to see, some angle that you haven't seen in the session, then by all means you can submit. All right, so again, today's topics are the following: unit conversion problems, hypothetical case rate problems, and mixture problems. So let's go ahead and get cracking on that. Okay, when we do problems, again, here's the story. I think if you've been to these study halls before, you're going to know this, but there are a couple of names that I don't think I've ever seen before. So if you are one of these new folks, you should see these buttons over there at your left. And smiley face if you see those buttons. These are the buttons that you should use to answer the questions. So when you're given a question, please answer questions with these buttons. Please do not answer questions in the IM box. And click the letter only one time. Because what will happen is if you click twice, then the second click will undo your original action. It will unselect your answer choice, and then you'll be blank. So please click only once. I think a lot of people, what I've seen is blinking letters, which means that people are clicking on these things like 10,000 zillion times. You just have to click it once. So if you click it twice, it'll go away. All right, let's go ahead and get started. And again, please use the buttons. Please do not answer in the text box. Here's your first problem. I will give you a timer, and we'll get going. Okay, ladies and gentlemen, please answer the question. It means if you have to guess, there's a lot of people who don't have guesses. If you have to guess, please guess. There's Adam, you don't have an answer, Damon, Kathleen 1, Pusha, Prob, and Pusha, now you do, and Viscott at Gmail. Okay, and remember, if any of you are new to this, do remember that this is the GMAT, and the GMAT does not allow you to not answer questions. So if you, here are the class statistics. It seems like the class is having not too hard of a time with this problem. But notice that there are 5 people listed as no answer here. What this means is that one of those people is me, but this means that there are 4 people who are not answering. So, I mean, not to sound like a second grade teacher or anything, but you have to answer the question. This is the GMAT. The GMAT does not allow you to not answer questions. So, make sure you don't forget this. Like on the GMAT, if any of you are new to this test, on the GMAT you must answer every question before you can move on. So if you are one of the 4 people who has not answered this question, then make sure you understand that you need to start doing that. I mean, I can't force you to answer it, but if you're not answering it, you're not doing yourself any good. Okay. This is a unit conversion problem. What that means is that you have to basically go from one unit into another unit. So the mass of 1 cubic meter is 800 kilograms. So when you have a unit conversion problem, there's basically 2 elements, the 2 main elements. The first main element is that you have an original given quantity of something that you have to convert. The other thing that you have in these problems as well is you have 1 or more conversion factors. What conversion factors are reference values that are equal. So if any of you are finance people, the easiest way to understand what a conversion factor is that it's the same thing as an exchange rate. Like for instance, an exchange rate, if $1 is 18.5 pesos from Uruguay, 1 US dollar is 18.5 Uruguayan pesos. What this means is this is just an exchange rate. This doesn't mean that anybody actually has $1, and it doesn't mean that anyone has 18.5 Uruguayan pesos. That's not what it means. It just means that you can convert. So conceptually, that's the difference here, is that the thing I'm calling number 1 is something that somebody actually has, and number 2 is not. So this is something that you like actually have, or at least theoretically. Versus the conversion factor is not something that anybody has. Like in an exchange rate, no one has to have these amounts of money. In fact, when you're talking about exchanging, you would definitely be dealing with more than $1. So these are not quantities that people have. They are just values that are equal. So in this problem, tell me in the text box, what is number 1 in this problem? Like what is the given quantity in this problem? Let's put that in a different color. Text box, please. Is it 800? Does anybody have 800 grams of anything in this, kilograms of anything in this problem? It's the one thing that most of you are not. Maybe you're not understanding what I'm saying here, because it's the one thing that most of you are actually not saying here. What I'm asking, I guess, is this. Which one of these numbers is not a conversion factor? Let's put it that way. So Adam and Stephen Mullen have, the one thing here that's not a conversion factor is this. 1 gram of the substance is not a conversion factor. Like 1 gram of a substance is what you actually have in the problem. And you want to figure this out before you get started. So in this problem, you have 1 gram. And you're trying to figure out what this 1 gram, how big would this be? So 1 cubic meter equals 800 kilograms. You don't have a cubic meter of anything. You have 1 gram. And this is just a reference value, and so is 800 kilograms. So, and also these are other conversions. Everything in green is a conversion. These things that are in green are absolutely not quantities that people have. So, I mean, smiley face if this makes sense. Because a lot of you guys input this, and it may have been a miscommunication issue. But in this problem, the way you have to look at this is I have 1 gram of this stuff, and I need to figure out how big it is. Nobody has 1 cubic meter of anything. Nobody has 800 kilograms of anything. Nobody has 1 kilogram. Nobody has 1,000 grams, and nobody has 1 cubic meter. And finally, nobody has 1 million cubic centimeters. These are not values that people have. It's kind of like if I have $158 and I want to convert it to Uruguayan pesos, then I have $158. I don't have $1 and I don't have 1850 in Uruguayan pesos. But I can use that as a conversion. So this is, if people have issues with these, then the issue stems from the fact that people are not identifying what do I have versus what is a conversion factor. So does this make sense? Smiley face if it does. Okay, so the way these work, and we're going to need a little bit more room for this, so I'm going to go ahead and import these onto the next page. Okay, the problem will go away for 2 seconds. It'll come back. Okay. All right, in this problem, the way unit conversions work is it's very systematic once you've figured out this stuff. So here's a way to do unit conversions. It's definitely not the only way, but it's a way that's consistent. The first thing that you do is you take the thing that you have, so the starting value, i.e. the quantity that you actually have, and put it on the left. So in this case, that value on the left is 1 gram of whatever substance. Then the deal is that conversion factors become fractions. So make each conversion factor into a fraction. So for instance, this conversion factor would be one of 2 fractions. It would either be 1 cubic meter over 1 million cubic centimeters or vice versa. So let's put those both in there. Like as a fraction, this conversion factor either looks like this. It's either 1 cubic meter over 1 million cubic centimeters, or it's 1 million cubic centimeters over 1 meter, cubic meter. And then the way that you decide which way these fractions should go is the idea is you want to cancel your old units and you want to replace them with the new units. So what you do is you multiply by these fractions. And choose whichever fraction will kill the old units and leave the new units. So for instance, we need to get rid of grams. So here's a fraction that involves grams. It's 1,000 grams is 1 kilogram. So where should grams go? Should we put grams on the bottom of that fraction, or should we put them on the top of it? Text box. Where should the grams go? The grams should go on the, a couple people are saying top. The grams should go on the bottom because we need to, okay, like if something is outside of a fraction, it's by default on top. So what might help you, if you're one of the people that said top, it might help you to understand that this is 1 gram over 1. And so to cancel the grams, we absolutely need grams at the bottom. So we know that 1,000 grams is 1 kilogram. If you put grams on top, you wind up with grams squared divided by kilograms, which is nonsense. So especially the couple people who put top, smiley face if you understand what we're doing here. We have to make that cancel, because we don't want grams anymore. We want grams to go away. So, and then now we have kilograms. We don't really want kilograms either. So the next fraction is we can go from kilograms to what? Text box. Where can we go from kilograms? We can go to cubic meters. So we need to kill kilograms. So kilograms on the bottom, cubic meter on the top. You can't go directly to cubic centimeters. So then this is the kilograms are going to get canceled. And the numbers are 1 cubic meter is 800 kilograms. And then finally, we don't want cubic meters either. So we want to cancel cubic meters and leave cubic centimeters. And the numbers are 1,000,001. And there's our and finally at the end of the day, once we cancel all of these things, we have these are the units that we actually want to have in the problem. We want like how many cubic centimeters? What is the volume in cubic centimeters? So that's how this works. I mean, it's sort of annoying, but it is what it is. So finally, you have to do the arithmetic. So the arithmetic that's left over here is 1 million divided by 800,000. You can kill zeros, and that just leaves you with 10 over 8. So this is 1.25 cubic centimeters. So that's B. In some of these problems, you'll have some eliminations based on common sense, although here, probably not. Because, I mean, if you understand how big things like grams and cubic centimeters are, you probably know the answer is not D or E, because those are awfully big for 1 gram of something. But A, B, and C are certainly all, like, not. A and B are very reasonable. C is a bit on the big side, but still not ridiculous. E is sort of ridiculous. But the other ones are all somewhat reasonable. Okay, any questions about this problem? Any questions about the procedure of unit conversion? So we have 2 more of these. And I mean, what's cool about this process is that it's not as, because I mean, if you can convert units more intuitively, then fine. Although under testing pressure, sometimes that intuition suffers. And the advantage of an approach like this is that even if your intuition takes a dip, you can still do this. Text box says, are we always going to be given conversion factors? In terms of things like metric units and stuff like that, yes. I think they will give you basically everything, except for time units. They won't tell you that there are 60 minutes in an hour, and they won't tell you that there are 24 hours in a day, and so on, because the whole world uses the same units. But with any other units that are not, the only units that are used in the entire world are time units. So you will have to know how many seconds there are in an hour and how many minutes there are in an hour and so on. Like, yes, that. But anything else, if there's any country that doesn't use something, then they'll give you the conversion. So, like, for example, Americans don't use things like cubic centimeters unless they're scientists. So therefore, for the benefit of Americans, they'll give you that conversion. People who are not Americans don't use feet and yards. So if the problem has feet and yards in it, then they'll give you that conversion for the benefit of people who are not from the States. So there's your answer. The short answer is yes, they will give you the conversion factors unless they are time. If they are time factors, then they will not give them to you. Is there yards conversion to feet is not provided by the GMAT? Is it really not? Do you have a reference for that? I'm looking through OG12, and there's two problems with yards in OG12, and the whole problem is in yards. You might want to check that because the word yard doesn't appear anywhere in the diagnostic test. So if you are, if you're the person who's the GMAT prep test. Let me do a quick check of an archive that I have. Just a second here. If you have the problem, that would be interesting to know, because I would be very surprised if they did not give you that conversion. But 1 yard is 3 feet. So if you have the reference for this, let me just type this in the text box. If you've got a specific reference for this question, I'd like to see it. Because they even tell people, I think that almost everybody knows that 1 kilogram is 1,000 grams, but they still tell people that. So I'm very surprised that they would not tell people yards. Unless the whole problem is in yards, then fine. All right, next problem, let's clear your answers and try, we're going backwards, try this. Here's your timer. Have fun. Again, guys, please answer with the buttons and not the text box. Okay, ladies and gentlemen, if you are Satish or Joanna or Bosha or Prab or Hema or Damon or Deval or Chander, then please answer the problem. Again, remember that, and by the way, for the person from the last problem, if you're going to email me that problem, here's your email address that you should use. Okay. Remember, this is the GMAT. I know I've said this 100 zillion times, but this is the GMAT, and you should, these are GMAT prep. All of today's problems, except for one, are GMAT prep. So that was GMAT prep. This is GMAT prep. The other ones, all of them are except for one problem, which is from our strategy guide. Okay. Remember, you can't not answer the problem. There's still a few of you who haven't answered the problem, and that's not an okay thing to do on the GMAT. But let's talk about it. So this is Let me go back and make one quick edit to this window here. This is the problem that you have. The original given quantity is it could be something that you have, or it could also be something that you want. So those are, because conversions are the same like forwards and backwards. Like if I have dollars and I want Uruguayan pesos versus if I have Uruguayan pesos and I want dollars, those are not the same. Those are not different. So, for instance, so let me just illustrate what I mean. Like quantity you have and quantity you want are the same from a math standpoint. For instance, if I say I have 2,000 Uruguayan pesos, how many dollars is this? And how I want 2,000 Uruguayan pesos, how many dollars would I need to trade? I mean, these are different from a conceptual standpoint, but from a math standpoint, these are exactly the same conversion. So when I say the quantity that you want, that you have, that also includes quantities that you want at the end of the problem, because they're the same. So smiley face, if this makes sense. I have 2,000 Uruguayan pesos means this is the quantity on the left. And also I want 2,000 Uruguayan pesos also means that's the quantity on the left. So in a problem like this one, instead of a quantity that we have, it's a quantity that we want, but this is still the given quantity. That's the given quantity. Okay. Hold on just a second. Okay. So the quantity on the left of this problem is 1,200 ounces of orange juice. So we want to have 1,200 ounces of orange juice. So statistics from the class. The class statistics are, people are kind of all over the place on this one. The majority answer, I think, is the correct answer here, but as you can see, people are having a decent amount of trouble with this. What we want to have 1,200 ounces of orange juice. So this is the quantity that goes on the left. So then everything else is conversions. So you have to be a little bit more careful here. And if you picked B, it means you're not being careful. This is not a conversion of 1 to 3, and that's what's important to realize. But 12 ounces to a can is also a conversion factor. So you have two conversion factors. The first conversion factor is that 1 can of concentrate makes 4 cans of juice, not 3. Be careful. Because you're mixing 1 can of concentrate with 3 cans of water and you're producing juice, which means that you're producing 1 plus 3 cans of juice. You're making 4 cans of juice. So that's one conversion factor. If you got B, that means you thought that was 3 to 1, which it's not. So there's your left. If you got B, then you did the math right, but you didn't read the problem carefully enough. The other conversion factor is that 1 can of anything is 12 ounces. So once we figure these things out, we can set the problem up. It's 1,200 ounces of juice. So make sure you don't just write ounces. It's ounces of juice times text box. We'll get that in a second. 1,200 ounces of juice times. We want to get rid of ounces. So ounces of juice has to go on the bottom. which means that can of juice goes on the top. So 1 can of juice is 12 ounces of juice. And then times, we've killed the ounces of juice. 1 can of juice makes, 4 cans of juice gives you 1 can of concentrate. So cans of juice, can of concentrate. And the numbers on that one are 1 and 4. So there's your arithmetic. So again, the first fraction cancels ounces of juice. The second fraction cancels cans of juice. That leaves us with cans of concentrate. So 1200 over 12 is definitely 100. So that means that's 100 over 4. So that's it. There's a question in the text box. Here's the question in the text box. I can understand where this question is coming from, but the best way to answer this question, the question is, how can we assume that a can of water has the same volume as a can of concentrate? The best way to answer this is to answer it with, what else are you going to assume? I mean, that's supposed to say possibly. What else could you possibly assume? I mean, this is an important lesson because the math section is not as heavy on things like common sense as the verbal section is, but if they give you a math problem where there's some technical ambiguity, then there's going to be some interpretation that is common sense. And I mean, if they don't distinguish one type of can from another, then it must mean. So it's like here, they don't mention any sort of existence of different types of cans. So the common sense interpretation here is that it's 1 can size. Because, I mean, if it were not 1 can size, they would very clearly have to tell you that. So if they don't tell you that, there's only one thing that could mean, which is that it's a single size of can. So the question in the text box, are these kinds of ambiguities common? No, not really. They're actually sort of rare. In fact, what's more common is for them to be really annoyingly specific and to like spell out things in a way that seems like it's more complicated than it really is. But if you get a problem that works like this, then you need to just kind of fire up the good old-fashioned street sense and kind of ask yourself, what would this mean if I saw it in the real world? So, I mean, in the math section, these things are not that common. But, I mean, remember that there are entire sections of the verbal that are basically tests of common sense. So there's a lot of that theme. And when I say that, I don't mean it in any sort of derogatory way. I mean, because a lot of people don't use common sense on tests. And so for those people, that's a new kind of approach. But there are some problem statements where you do have to kind of just use your real-world intuition and say, what's the only reasonable way to read this problem statement? Most people are like that. I mean, like if you look at other study halls, there are, like especially the strength and weaken study hall. I mean, strength and weaken is a test that heavily depends on common sense and that cannot be solved with rules. So, you know, it's people who do that soon discover that it's impossible to solve strength and weaken with rules. But I mean, there's not as much of that in the math section, but there's still some. So be on the lookout. I mean, if there's anything that you think is ambiguous in the math section, it is not ambiguous. I mean, not really. There'll be one way that makes sense. Okay. Any other questions about this problem? If not, we'll kill it. We'll move on to another one. Okay, I don't see anybody typing. So here's another problem. This one tends to be a little bit more challenging for people. This is data sufficiency. Again, please answer with the buttons. Go for it. Okay, let's make sure we answer this. A few of you haven't answered it. There's one newcomer who's asking where are the choices. This is a data sufficiency problem. These study halls do assume that you know how data sufficiency problems work. If you don't, then you should familiarize yourself with those before you watch this part of the study hall. Because it's a type of problem that we really wouldn't make a lot of progress if we had to re-explain it every time. So we do expect that you know how this type of problem works. If not, then, because it's half the whole math section. So if you don't know how this works, this probably means that you haven't really ever studied for this test before. So if that's the case, then get up to speed on how the basic problem format works and then come back. We have a couple of resources for that, or you can also just look in the official guide on pages like 267 to 269. Those are page numbers. Official guide 12, page 269, like around there somewhere. Okay. If you are Hema, you haven't answered the question yet. If you are Arun, you haven't answered the question yet. Remember, you guys have to answer the question. So please guess something. Okay. All right. Here are people's responses. Okay, remember if you click twice, it'll undo it. So you guys didn't have answers on there, which means you probably clicked a second time. If you click a second time, it'll undo your other answer. All right. Okay, so here's what people did. Majority of D, but still a large number of other answers too. Let's take a look. What's going on here is that you've got a question that's in miles, but then you've got kilometers. So what should be clear is that you have to convert stuff. So you have to convert either miles to kilometers or kilometers to miles. Which one of these things do you think would be a better idea? Yeah, probably miles to kilometers, because if you have to go from kilometers to miles, then you have to do twice as much work. Because like notice that there are two things right now that are already in kilometers, and there's only one that's in miles. So we might as well do that. So what you've got to notice about this problem is that there's two ways to approach this. The first way is to phrase this in terms of speed. The second way is to use a conversion. So I mean, I'll show you a regular conversion way. So the first thing we need to do is get this 10 miles out of miles. So first, kill the miles. So 10 miles times, we need to get rid of miles. So 1 mile is on the bottom of the fraction and 1.6 kilometers on the top of the fraction. So that's 16 kilometers. And then just figure out what's going on. So statement 1. With statement 1, the average rate is less than 6.4 kilometers per hour. So we need to figure out how long. Sorry, I didn't write 16. 16 kilometers. In each of these statements, if you approach it this way, this is the given quantity. Because this is the number of kilometers that you are actually supposed to walk if you are pay. And the other things are just speeds. Speeds are also conversion factors. So this is statement 1, you have your 16 kilometers. And then you have less than 6.4 kilometers per hour. So what you can do with that is 1 hour per less than 6.4 kilometers. You can totally do this. So what happens when you divide by less than? And notice these numbers are all positive, so we don't have to worry about it. If you had to worry about negative signs, this would all go nuts. But when you divide by a number that's less than something, do you get less than or do you get more than? Text box. You get more than. And if you don't see why, then try a couple numbers and see. So this is going to give you more than. And then we have to just do the arithmetic. So the kilometers are gone, and so 16 over 6.4. We have to do the arithmetic. You guys see how it's going to work out. So that means 160 over 64, which looks like we can divide that by 16. So that's 10 over 4. That looks like it's more than 2.5 hours. So this is going to be sufficient because the question is, did pay take more than 2 hours? So this would be sufficient because that's a yes. Notice that if this were less than 2.5 hours, it would be insufficient. So inequalities are not symmetric this way. Like if you solve an inequality and it points the other way, then things that are sufficient usually become insufficient. So you have to do the work. If this were an equation, you would just be able to do the conversion and say, because it's data sufficiency, I don't have to do the work. But because it's an inequality, you have to do it. Statement 2, we have 16 kilometers. Times 16 kilometers times, it took pay more than 9 minutes per kilometer. So this is a little bit more straightforward because the thing's on top. More than 9 minutes per 1 kilometer. So this is more than, greater than 16 times 9. So that's greater than 144 minutes. 144 minutes is more than 2 hours. You don't need to convert this to hours because that would be sort of painful. But this is more than 2 hours. So yes, it's sufficient. So overall, D like dog. Any questions? There's another way that you can approach it if you treat it as a speed question instead. Let me just find you a link. Just a second while I look for this. Okay, here it is. On this question, there's another approach that I don't want to present here because so that we can get to some more topics. But if you want an alternative approach, I'll put it in the text box. There's a forum thread. On that forum thread, there's an approach where speeds are used. So if you want an alternative approach to this problem, go ahead and check out that forum discussion. Any questions on this approach to the problem? So, and then notice the other thing that you want to notice here from this problem before we move on to a new topic. The other thing that you want to notice here is that, which is a much more general lesson, is when you have data sufficiency inequalities, you always have to do the work. Because you're not going to be able to tell which way the inequality turns out. I mean, this is important because with equations, a lot of the time you can skip doing the work. But here, like for instance, if statement 1 turns out to be sufficient. But if you change less to more, it becomes insufficient. Also, statement 2 is sufficient, but if you change more to less, then it becomes insufficient. Also, if you leave 9 alone, but change, sorry, if you leave the more alone, but change 9 to 7, it also becomes insufficient. So these are not things, I mean, you can't see that these work out this way unless you actually do the work. So the point is that you can't be lazy about this. With equations you can, because with equations you can do things like, oh, I know this will have a solution, so haha. But with inequalities it matters like what the numbers are and which way the inequality points and all these other things that you can't tell ahead of time. So you always have to sit down and do the work with inequalities. Questions? If not, we'll look at something new. Okay, someone is typing something, so let me wait just a second. If you have text in your text box and you're not typing, then make sure that you erase it so that we can move on. Steven appears to be typing something. So we'll wait for that. Let's see. Someone typed, how should I answer the question? Not sure what you mean. If you mean what was the letter answer to this question, then the letter answer was D, because they're both sufficient. So that means that it's D, if that's what you're asking. Oh, Stephen, if you use that shortcut at all on data sufficiency, you're going to die. Like that shortcut on data sufficiency will pretty much give you the wrong answer 100% of the time. If you watch the November 4th Thursdays lecture for more on that. But if you even think about using n equations, n variables, you're going to get killed. Should I select the letter or click on the on data sufficiency? On problem solving you might get away with it, but watch that lecture, you'll see what I mean. Hema, these things are buttons that you press. So you just click on them exactly one time. So yeah, it's November 4th. The lecture is entitled Problems on Which Traditional Algebra Does Not Work. Okay. Let's move on, ladies and gentlemen. Why did I change it to more? Well, I didn't change it. Oh, you mean in this part. If you divide by less than something, then that gives you more. If you don't understand that, then make sure that you try. Make sure you know how math operations affect these kinds of things. Make sure you know how math operations affect inequalities. For instance, if I divide 10 by a number that is more than 2, then that's less than 5. I mean, if you don't see how this works, then just try enough examples until you see how this works, because you want to develop an intuition for this stuff. You don't want to have to work it out from first principles every time. But just think about 10 over 3 and 10 over 4 and 10 over 5 and 10 over 10 zillion trillion, and then you'll see what happens. I mean, also play around with numbers like 2.000001. But the goal is to develop intuition about how these kinds of things are going to work. So if you just look at enough examples, eventually you'll understand how they work. If the numbers can be negative, then it all goes to hell. But in a problem like this, it's a word problem with distances, so they can't be negative. All right, let's try this problem. This is from our GMAT strategy guide. Oh, okay, yeah, you're the one who submitted this, aren't you? Also, I'm going to give you answer choices. Say you have, I'm going to add in answer choices. They'll appear in a second. Okay. Here are your choices. Here's a timer. Maybe a little bit longer on the timer because there's a lot of words. Okay, everybody pick something. We're pushing 3 minutes here. So, okay. What I want to do here is I'm going to try to bridge a gap between two things. And those are, number one, presenting a method that I've already kind of presented before, and B, trying to still summarize that method for people who haven't seen it before. So, like, these are, of course, rate time distance problems. So this is a RTD problem. So what I'm going to do here is, first I'm going to give you a date reference. There's a Thursday lecture from April 29th, 2010. In the April 29th, 2010 Thursday's lecture, I gave a general approach to these. 7-step approach to these problems. So what I'll do is, in discussing this problem, I'll recap that discussion. And then what you'll notice is that it also ties into this discussion of mixtures that we're going to have. There's a prob and there's a portende who haven't answered the problem. Make sure that you answer it, please. Okay, or at least remember, I can't make you answer it, but this is the GMAT. You have to answer the problems. If you don't answer the problems, you'll sit there and stare at them until you answer them. Okay, let's check this out. So this is going to be, I'll walk you guys through what I did in that other lecture. But here's a 7-step approach to rate, time, distance type problems. And what we mean by rate, time, distance, type, that's going to become apparent in a second. It's not just rate, time, distance, but there's other problems as well that this can work for. The first is you want to make a chart. So the chart is the same chart that the strategy guide talks about. So rate, time, and distance goes on top. Rate times time equals distance. And then whatever components exist in the problem you want to put into a column. So what you have to do is analyze the problem to see what are the different components of the problem and then put them into a chart. So the components are, one of the things is the actual trip that happened, and the other one is the hypothetical trip that would have been a little bit slower. So one component of the problem is actual, that gets a row. One component of the problem is hypothetical. I mean, notice that there's a lot of ways that these problems could have components. Like in this case, the components happen to be actual and hypothetical. But, you know, you could have another problem with 2 people traveling whose names are Bob and Joe, and then the components of the problem are Bob and Joe. So, I mean, anything that is a logical division of what's going on in the problem. Then, okay. What happens next is you want to put concrete numbers in the chart. So what I mean by concrete numbers in the chart is numbers that actually belong in one of these 6 boxes. So you have to be careful, because this 5 miles per hour is not a concrete number. Like, nobody is driving 5 miles per hour. Instead, this is a relationship between the two speeds, but it's not actually a number. The only concrete number here is 30. And, I mean, when you have a hypothetical situation, what you need to realize is that in a hypothetical situation, something will still be the same. That's how hypothetical situations work. So in most, I won't say every single one necessarily, but in most hypothetical situations, you're keeping one thing the same and theoretically changing other things. So in most hypothetical situations, something stays the same. So you have to figure out what this is. Because, I mean, it wouldn't make sense to have a hypothetical situation where everything was different, because then there'd be no hypothesis. Like, there'd be no comparison to make. Because when you have a hypothetical, what you're doing is you're saying, if this same situation had turned out in some other way. So something has to be the same. That's kind of where we're going with that. So in this case, what stays the same is the distance, because you have to get that from the context. But if he had driven the same trip 5 miles per hour slower. So smiley face, if this makes sense so far. Smiley face icon that's over there. If this is all good so far. Okay. Now we've got step 3 in my 7-step method. Is if anything is still unknowns, and I mean things should still be unknowns, you're probably not going to get all arithmetic numbers, but specify relationships between remaining unknowns in words. If you have things that are not unknowns, you don't need a relationship. So like in this case, you don't. For the 30 and the 30, those are known quantities, so there's no need to talk about relationships there. But with the rates are unknowns, and the distances are unknowns, so we need to state relationships. So as far as why do it in words and not variables, that's what we're going to get into now. So relationship. Okay, we don't need that to be two lines. It's kind of silly. Relationship. And I like to actually put them in the chart. So the relationship between the rates here is what's the relationship between the actual and hypothetical speeds? In words. Text box, please. How are the actual speed and the hypothetical speed related? Yeah, the actual speed is, I mean, don't just say one is 5 miles per hour faster. You need to say, and we don't want variables yet. The actual speed is 5 miles per hour faster. So actual is 5 miles per hour greater. We want to do this in words. We'll talk about why in a second, but it's very important not to put variables in here at this time. What about the times? What's the relationship, text box, what's the relationship between the times? Be careful here. Make sure you know what I'm telling you to be careful about. 4 minutes, but remember that nothing else in this problem is in minutes. So what do you have to do with that 4 minutes? I mean, you guys are all right, except for the people who are writing variables. Don't do that yet. No one's done this yet. What do you have to do with that 4 minutes? Yeah, you got to make it 4 over 60. Because if you don't make that 4 over 60, then you will have to convert everything else in the entire problem to minutes. And you don't want to do that. You really don't. So, because you don't want to make this miles per minute. So instead, I guess you could, but who wants to do that? So, okay. The relationship here is that the actual, because I mean, you'd have to make, I guess you could do that. 5 miles per hour would become, well, let's go there in a second. The actual time is 1/15 of an hour less. And I mean, it better be, by the way, make sure you make these things greater and less. Because the problem with the word faster is that it's easy to get confused. Because remember that faster could mean time or faster could mean speed, and they have opposite meanings. So like, remember, faster means less time, but faster also means greater speed. So be very careful with this. I wouldn't use the word faster. I would use the word less or greater, because faster is really easy to get confused by, as you can see. So now let's talk about why would you want to do this in words. There's two reasons why you want to do this in words. The first reason is if you do this in variables, you're going to wind up with two variables, and then you're basically dead. Like if you get two variables in this problem, you will not finish the problem. The second thing is that this is what, if you put words here, this is diagnostic. Like if you can't put the words here, that will point out exactly what you don't understand. That's the big deal here. If you just have a bunch of algebra on a page and you get it wrong, you will have no idea where you went wrong, because there's just a bunch of meaningless symbols on the page. On the other hand, if you can't write these, then that is exactly where your problem is, and you've found it. That's your problem. So make sure that you do this. Then once you're done with those words, take one of those sets of words and make a variable out of it. So make a variable from one of these relationships. Do not make two variables, because if you do, then that's going to be a serious hit to your time bank. So it doesn't matter which one we use, but for the sake of fun and kicks, let's go ahead and use the one on the left. So the actual one is 5 miles per hour greater, which means actual speed can be rate plus, let's use r for the actual rate, and r minus 5. Ioana, I don't really understand the question. I mean, in this case, the problem is the relationships are all between the actual situation and the hypothetical situation. So no, it's not just actual. If it were just actual, there would be no relationship. The reason I'm choosing R for actual here is because that's what they're asking. So how fast was he actually driving? So let's put a variable for that. Now, here's the little secret here is that you don't need a second variable, right? Because you have a relationship. It's called R times T equals D. So use R times T equals D to fill in the rows. So this is 30. R times this box equals 30. So what is this box? Text box, please. What goes here? In this time box. If that's 30 and that's R, then this is 30 divided by R. You don't need another variable. So yeah, you don't want T. Again, this is in capital letters here for a reason. Do not define a second variable. If you do, you won't finish the problem. So 30 divided by R, because the distance divided by rate is time. Also, this is 30 over R minus 5. So there you go. Once you've done this, you should wind up with a relationship that you have not used yet. And what you can do with the unused relationship, the one that's left over, is you should have a relationship left over. Use this relationship to write an equation. So in this case, the relationship that's left over is that the actual speed is 1/15 of an hour less. The actual time, rather. It's 1/15 of an hour less. So we can write the actual speed is 30 over R equals the hypothetical speed plus 1/15 Um, so there. Now, this is a quadratic. What you can do that I don't want to do here on this study hall, because this is not an algebra study hall, is you can solve the quadratic. I mean, the short explanation for this is that you can multiply by a common denominator. It'll produce a quadratic. And the strategy guide shows you how to solve the quadratic. I don't want to spend like 10, 15 minutes of a study hall solving a quadratic. So instead, what I'll show you is another thing you can do, which, remember that there are answer choices. Yeah, you can just take the answer choices, and you remember the answer choices were 30, 35, 40, 45, and 50, and you can just plug those in and see if they work. So, and the seventh step, by the way, is solve. Sorry, that should be on there. Seventh step is solve the equation once you have it. So, step 7 is solve. Okay. Yeah, you don't want to skip that step. Or, well, if it's data sufficiency, you might be able to. Remember, this is not data sufficiency, but yeah. So, or just plug choices. So, like, if you do, like, let's say you try A. That gives you 30 over 30 equals 30 over 25 plus 1/15. This doesn't work. I mean, if you try it, it doesn't work, etc., etc. Long story short, if you try D, then 30 over 45, which is 1/3, equals 30 over 40. Sorry, if you try 30 over 50 equals, if you try E, I think it winds up being E, 30 over 50 equals 30 over 45 plus 1/15. This winds up being 3/5 equals 2/3 plus 1/15, and that's true. No, it's back. These are supposed to be minus signs. Hello, stupid. There's a mistake here. This is supposed to be a minus sign. This is because this is the faster time. So this is a bigger number. So the actual time is smaller and the hypothetical time is larger. So my bad. Again, this is the smaller time. This is the larger time. So it pays to double check those things with signs. So, but this is still a fail even with the minus sign in it. So A fails, B fails, C fails, D fails, E does not fail. 3/5 really is 2/3 minus 1/15, because 10/15 minus 1/15 is 9/15. So the actual is 1/15. This is 1/15 of an hour. This 4 minutes is right here. So he would have arrived at work exactly on time. So that's a difference of 4 minutes, which is 1/15 of 1 hour. Other questions? I mean, okay, yeah, this winds up being the last choice. I mean, I just made up choices because in the strategy guide they give it to you as without choices. Unfortunately, because I mean they should give you choices so that you can practice plugging in as well. If you think the quadratic is easier, then that's great. I mean, I don't, you do. We're both right. Like for me, the quadratic would take about 6 times as long as plugging in fractions. For you, the quadratic might be faster. The point is you should be able to do both. That's the point. If you are ever worried about which one is faster, you are thinking about the wrong stuff. So, the answer choices are up here. I mean, I just made them up, but there they are. 30, 35, 40, 45, 50. Ricard, don't use 2 variables. If you do, it'll take you like 4 times as long. So try to use one variable. Okay, let's move on. Remember that this is mostly, at the end of the day, an individual learning exercise, so it's probably not worth the time to go back to look at how other people did. Let's take a look at, I thought I had one more of these here. Yeah, okay, try this problem that's right here. Okay, there's your answer, there's your breakdown, but it doesn't really matter how people did, it just matters how to solve it. Okay, try this. This is data sufficiency. Scores are not scaled according to how people do. So it does not matter how your peers answer. Forgot to give you guys a timer, so here's a timer with some time left on it. Okay, ladies and gentlemen, boys and girls, this appears to have been a lot easier for. By the way, one thing you'll notice is that in our strategy guides, the last few problems of each word translation chapter tend to be really super obnoxious. So, and the disclaimer is that a lot of those problems are much harder than anything that would show up on the real exam. Interestingly, that last one's not. There is a problem from GMAT Prep about like currents in a boat or something like that, that is just as obnoxiously hard as that problem is. I'll try to find it. Let's see. I may not be able to find it in 5 seconds, but if I can, I'll put it up. Yeah, hold on a second. Okay, that is, okay, I can't find it. But there is one that's a lot like that one. It's upstream and downstream question. If you search for search on the forums for that, you should find it. Okay, anyway, with data sufficiency, the deal is you want to make if necessary, you want to make a chart. Here's the statistics. Statistics are here. Nobody picked A or D, which is good because it should be clear that statement 1 is not sufficient. So let me get those off the screen. But most people picked, let me make that smaller. Most people picked, nobody picked A or D, so good. So A and D, statement 1's not sufficient. Ordinarily you would want to make 2 charts, 1 chart for each statement. But statement 1 in this case hopefully is fairly clear without having to make a chart. So if both statements require work, then you should make separate charts. It's a mistake to try to put statement 1 in the same chart as statement 2. So what I was saying is that, like, in this problem, it should be quite clear that statement 1 is insufficient, because there's no information at all about the last 200 kilometers. So you only need 1 chart. But if both statements were, like, substantial, then you'd want 2 charts. Because remember, you don't get an eraser, so you can't do the work for both statements in a single chart. In any case, okay, statement 1 is not sufficient, so that's good enough. Statement 2, well, okay, so here's a chart. We have, if it had been, that indicates that we're dealing with a situation that's hypothetical. So let's make a chart for that. That means that we have 1 row for actual and 1 row for hypothetical. And you have rate times time is distance. So actual rate, we don't know. We know that it's 400 in both cases, so they're concrete numbers. So again, let's write out the steps that we're doing. Step 1 is to make the chart. Step 2 is to put concrete numbers in the chart. Step 3 is relationships. We don't need a relationship between 400 and 400 because, you know, those are hard numbers. But so the relationships in words, the rate, if the car's average speed had been 20 kilometers per hour greater. So this means that the hypothetical is 20 more. The relationship for time is that the hypothetical time is 1 hour less. Also, make sure that you check these with common sense. Like, if you got that this was more and that this was also more, you should make sure you know that that's impossible. Because if you take more time, then you would have less rate. Like, if you travel at a higher speed, then you are going to take less time. And if you travel at a lower speed, you're going to take more time because it's the same trip. So you should make sure to subject these answers to a certain amount of common sense when you find that. Okay, let's make a variable. How much time did it take? So if we do something like t for this time, then that's, I generally like addition better than subtraction, so I'm going to put t for hypothetical. There's nothing wrong with it for actual. I just like plus signs better than I like minus signs. So the actual time's longer. So step 4 to find a variable. If you're the 2-variable guy, I'll try to answer your text box question after we're done here. But make sure you know that 2 variables is an inferior way to do the problem. Okay, step 5, use the r times t equals d. So that means division again in this case. So this is 400 over t plus 1. And that's 400 over t. So then step 6, you should have a leftover relationship. So let's use it. Leftover relationship should give you an equation. So that gives you, here's my leftover relationship. So hypothetical is 20 more than the actual. That means that 400 over t is that plus 20. What you want to do here is you want to solve far enough until it becomes apparent that there's going to be one solution. So, I mean, if you have enough number intuition, you might realize right now that there's only going to be one positive and one negative solution to this. If not, then you want to just go as far as you can until you figure that out. So step 7 is to solve. So if you do this, let's multiply by t plus 1 on both sides. I don't want to put it on the left, so there's both sides. So you wind up with 400 t plus 1 equals 400 t. If you don't, then you have to, I mean, like I said, you would need a significant intuition to figure that out. Like, you have to handle a lot of things. It's easier to just do the work. So the best answer to that is just do the work. It's definitely the least dangerous way to do it. Plus 20 t plus 1. I mean, yeah, if you know that one of them is going to be negative, then you're done. You're scot-free. But if you don't, you have to do the work. So it's if you are ever in doubt, then do the work, because it's better to be certain than not to be certain. So this is, let's divide by 20. So 20 times t plus 1 equals 20t plus t plus 1. So 20t plus 20 equals 20t plus t squared plus t. So that means that t squared 0, let's move it to the right-hand side, 0 equals t squared. The 20t goes away, plus t minus 20. At this point, you can stop solving because this minus sign means that you're going to get one positive and one negative solution. So if you know that, you're done because the negative solution doesn't count. So the fact that you get one positive solution is sufficient. I mean, at this point, you're not very far from the finish line anyway. So if you don't have that realization immediately, then it should only take you another 15 or 20 seconds to finish solving the problem. But when you get to this point, if you do have a quadratic that ends with a minus sign, that does mean it's going to be 1 plus and 1 minus, because that's how quadratics go. So if you do figure that out, then there's your answer. If not, then you just find the numbers themselves, which are 5 and -4, and you just kick out -4. Sorry, they're -5 and +4. So you'd kick out -5 and keep +4. Okay. Any questions here? Questions? Well, this work seems unnecessary. Well, again, if you have a certain amount of intuition, then the work might be unnecessary. But it's from a teaching standpoint, it's not wise to approach problems assuming a certain amount of intuition because you can't teach intuition. So, I mean, but if you have that kind of number sense, then by all means you should use it. Yeah, of course. Especially on, I mean, but be careful. Yeah, it depends on the problem. So, Stephen, make sure you go watch the lecture from November 4th, because those are a bunch of problems where if you skip the work, you will absolutely get all of them wrong. So, be conservative about that. Like, data sufficiency is mostly geared towards kind of annihilating people who just sit there and make assumptions. So, I mean, there are some problems that you can get with things like that, but there's a lot more problems that will get you. So, especially on data sufficiency. So, watch it. Especially watch that November 4th. Also watch the coordinate geometry data sufficiency ones. Those have some problems like that too. So there's 2 lectures on coordinate geometry DS. You might want to check those out. Okay. Milan, I think your name is pronounced Milan. You can email me that question if you want, and I'll look at it because we can't do OG here. So. Okay, it looks like we're definitely done. We're over by a few minutes here. It looks like poor old mixture problems got bumped again. So these are going to go to either next time or the time after. We've had 2 quant sessions in a row now. So if we do verbal next time, then we'll kick these to the time after that. The short version, let me just give you the super duper short version of this. Here's a mixture problem. And let me just show this to you for like 2 minutes. The deal with mixture problems, the short story with mixture problems, and I mean, frankly, if I give you the short story, then we won't have to do it in a study hall. The short story with mixture problems is that mixture problems are RTD-style problems. Because the deal is that, remember, you have a chart where the chart used to say rate times time equals distance. Okay, that's what the chart used to say. So the only difference with the chart now is that instead of saying these things, it says different things. And now it says % of fat. times amount of total gallons. That was not very well said. Times total gallons equals gallons of fat. But I mean, it's still, from the standpoint of the math, you don't care. Because in both of these cases, it's still blah times blah equals blah. So you can still follow exactly the same relationship every time. So you can still follow the same 7 steps. So in this case, we have like, you know, the 1% grade. We have the 2% grade. We have the 3% grade. And we have the mix. And so the setup, so there's your chart. Remember, this is the top row of the chart now. So the percents are hard numbers that you can fill into the chart. So this is 0.01, this is 0.02, and this is 0.03, and the mix has to give 0.015. So, and then you still have a relationship. So the relationship between the total gallons is the 1 plus, the first plus, the second plus, the third equals the mix. And the relationship between these is also the first plus the second plus the third is mix. Those are your relationships, because you can add gallons of stuff. So once you have this, they give you X, Y, and Z. So X gallons of this and Y gallons of that and Z gallons of this. That means that this is automatically X plus Y plus Z. Then you just do your multiplication. So that's 0.01X, that's 0.02Y. That's 0.03Z. And then that's, you can also add those. So then this time your leftover relationship would be actually the R times T equals D, because you haven't used that yet here. So that's a new twist here, but I mean leftover relationship this time is actually R times T equals D. Well, it's not rate and distance anymore. This times that equals that. So 0.015 times X plus Y plus Z equals 0.01X plus 0.02Y plus 0.03Z. And then you just solve. There you go. Okay, we definitely have to kill it. But the story with mixture problems is that they're just like rate problems. So you can use the same steps that we gave earlier for rate problems if necessary. There you go. So that means we don't need to do a session on rate, because mixture problems are now incorporated into this session. So, bang, mixture problems. Okay, so there's your total summary of today. Unit convergence rates, mixtures. I really got to wrap it up here, guys. But if you have super duper quick questions, then we will grab that. I'm going to stop the recording at this point.